This bad boy right here is the Gigabyte G1 980 Ti graphics card. And about 4 years ago, I actually went and reverse engineered the LED system on this. You can see here, we've got this big WindForce logo here. That one lights up. There's two ones on the side. And I wanted to be able to control this bad boy from my Linux operating system, but the only software available for it at the time was a old, outdated 2015 Windows application that was 32-bit. So I decided to go ahead and reverse engineer the LED system, and this video is going to be about that process. The end result of all of that work was this. You might be surprised that with reverse engineering, the implementation that you come up with at the end can sometimes be pretty inconsequential compared to the hours and hours of process that you dedicate to figuring out how the thing actually works in the first place. Here's a demo that I made from when I did this project. Essentially, all this script I wrote does is associate one of those colors that you enter as a command line argument with one of the values in its associative array. Now, this array actually corresponds to an I2C register. And don't worry, we'll get to I2C later on in the video. But for now, this was the final product. And as you can see, I'm using Bash on Linux to change these colors and not OC Guru 2. Just as a side note though, is this not the most beautiful graphics card that has ever been designed? I honestly believe it. I mean, look at this thing. This is a beautiful graphics card. This, in my opinion, was the pinnacle of graphics card design. That's the back of it right there. If you slot it in, you can see the SMDs on the back of the GPU die through this little window here. It's got a G1 watermark on it. You know, it's two slots, it's tasteful. It's just such a beautiful card.
Let's see Paul Allen's card. Look at that subtle off-white coloring. The tasteful thickness of it. Oh my god. It even has a watermark.
Comment down below with what your favorite graphics card design was. So this right here is the paper that I did up for this particular project. And now, again, with reverse engineering, it's often the process that is actually far more valuable than the end software product that you release. And so with reverse engineering projects like this, I always find it helpful to write up a document that describes the reverse engineering process so that other people can come in and understand how you got to the conclusions that you got to. So essentially, I've titled the paper Reverse Engineering the Gigabyte G1 980 Ti LED System and OC Guru 2. OC Guru 2 being, of course, the software that Gigabyte ships to change the lighting colors on this. So the first thing I do is do my acknowledgement. So there was the Open RGB project. That's the biggest sort of open source LED lighting project. And Adam Hans from that project had reverse engineered Aorus engine, which was the sort of follow-up to, or the replacement rather, for OC Guru 2. And now there were some similarities with that, so his process was quite helpful. But there were enough differences to make the process quite challenging in any case, as there always is with this kind of thing. So a couple definitions. OC Guru 2 obviously is a software. Decompiler takes apart software and lets you inspect a recreation of the original source code. APIs, you should all know what this is if you're watching this video. And then I2C is the final thing here that I will introduce later on. It's a communications protocol very commonly used by embedded devices. It's one of the big three sort of wired protocols in embedded, being I2C, SPI, and USART. So anyway, the first step with any of these projects, right, is to sort of get an understanding for how the things that you're trying to do actually work. So like there's three LEDs with this particular Gigabyte card. There's the big WindForce logo in the top, and that's the one that actually changes color. There's a silent fan indicator and a stop fan indicator. I don't particularly care about these two. I'm mostly interested in these ones because I think these two are actually automatic. So a couple of things that I noted right off the bat was that the LED systems weren't persistent. So every time I shut the device down, it'd start back up as the original white color. So that kind of tells me, okay, it's not being stored in any kind of non-volatile memory. The default values were, auto, and the brightness is 100%. And more importantly, this particular card right here didn't actually support 16.8 million colors. It had about 8 or so that you could choose from. But 7, here we go, 7 available that you could choose from, but you couldn't set sort of an arbitrary value for that, if that sort of makes sense. But yeah, by the way, This project, like I said, 4 years ago, so go easy on me, all right? My latex skills have gotten quite a bit better since then, so just be kind. The tools that I used for this particular one were quite interesting. So the two big hitters were API Monitor and OllyDbg, and I'll show you guys those ones in just a minute. I also use Ghidra and Snowman. So Ghidra is like the NSA's one, and I was just using these ones, they're decompilers essentially. I was using them to mess around, sort of try and figure out how stuff works, but these two were actually the ones that were super valuable. So API Monitor, absolute clutch. Like it lets you spy on like calls made to external DLLs that a program is utilizing, and those were actually key in this particular project. And then OllyDbg sort of lets you step through the program as it's running, set breakpoints, view function calls, things like that. So we'll get to that. We'll get to that. So OC Guru 2, right? The actual software that I wanted to reverse engineer. This is one of the more important things to get an understanding of. So like down here, for instance, this was where the LED settings actually came into play. So I could choose a style. So there was like, breathing, flashing, double flashing, and just a solid color. The brightness and speed, so the speed for the breathing and the flashing, and the brightness for just standard, right? And then some other special modes. I decided for this particular one, I would choose a minimum viable product of just getting this none style to change color. And because that's very important, because you can get very, very mixed up in these things if you don't have a starting goal. And I talk more about that in another video I did called How to Start a Software Project. But essentially, it's the same thing with reverse engineering, right? Like if your scope is too big, you're going all over the place. It's very hard to narrow down the specific things that you want to actually look at. So that's kind of what I wanted to do with this whole thing. So the next step, I actually went and had a look at the program files for this particular program. So OC Guru 2 installs to this location, right? And there are a couple of DLLs in here, and there's the executable itself, of course. But turn your attention to these DLLs, right? So we've got GV BIOS lib, GV crypt, I imagine that's cryptography, like some sort of encryption library, GV display, GV fireware. Now I'm pretty sure they misspelt firmware here, or Firewire. No shot, it's Firewire. So I'm guessing they just misspelled firmware, but those ones are interesting ones like to just have a look at. So, and essentially with this first part of the reverse engineering process, you're scoping out all of your particular targets. So I'm thinking, well, any of these DLLs might be involved with setting the LED colors. So that's what I wanted to figure out next. So you see what we do here. And I also did something that I thought was quite clever at the time, which was the release date of the 980 Ti was the 2nd of June 2015. So I thought any file in here that was modified before that date could not have been relevant in this at all. Now, technically, they could have reused the LED controller from an earlier card, but that's probably quite unlikely. So I think for the purposes of cutting down the scope in the initial stage, I think that was a pretty fair decision to make. So anyway, yeah, so these ones here and GV VGA config I must have missed, but yeah, those were the ones that were really interesting to me. So the next part now is to actually kind of have a look at the program and see what actually happens. Like when I press this button right here to change the thing to red, and you know, on the actual GPU itself, this thing changes to red, what does the software do? Because this is one of the key things to note about reverse engineering hardware devices, especially when software is involved. The software is going to do something that causes a change in the hardware at a very low level. And the key is understanding how it performs that. So it goes from a very high level environment, that's a Windows application, to a very low level environment like the light controller on a graphics card. So how does that actually happen? That's the key to finding out the entire project. So I have a look at these libraries further, and again, ignore my woeful latex skills at this point, messing up this entering here. But essentially, you can, like the next step, after I had a look at these DLLs, and I had a look at them more in general, so gvdisplay.dll was VGA APIs, which is very interesting. GV BIOSLib, BIOS library, of course. GV Firewire had to-do file description as the details. And then this one had some Chinese characters. The Chinese characters translated to dynamic link library, so nothing new there. But yeah, so now I want to actually find out, are these DLLs being called? And if they are are they relevant to changing the LEDs? Like, do any calls from these libraries right here have any impact on changing the color of the LEDs? So in that case, I loaded up the program in OllyDbg, and I actually have a virtual machine over here that has OllyDbg loaded up with OC Guru 2. Now, of course, this is a virtual machine, and the card is sitting right here in my hands. So OC Guru 2 won't actually start up and run. But what I want to show you guys right here is how to actually figure out what function calls all of those DLLs export that OC Guru is able to use. So over here in View, I can click on this window called Executable Modules. It might be a bit hard to see. Let me see if I can... yeah, kind of. But okay, so you can see here I've got ocguru2.exe, gv auto update, bioslib, osd, crypt, vga config. So all the DLLs that I was really interested here. And I'll just get rid of that because that is very, very laggy. But yeah, so I can have a look at what function calls these all export. So if I right click and I go view names, it'll give me a listing of all of the function calls that this DLL exports. So if I scroll down, there's actually nothing really interesting here except these ones. So these calls right here, you can see I've got something like flash BIOS A, get EEPROM, init bioslib, and these are interesting, but they're not actually what I'm looking for. The real moneymaker was when I got to gvdisplay.dll. So if we have a look at the names for this particular one, and we scroll down right to the bottom. Now, these ones are where things get interesting, because if you have a look right here, guys, and I will get back magnifier for this because I want you to be able to see it. But if you come down here, what are these functions right here? GV is logo light, GV is SLI light, and then what's this down here? GV set SLI light, like these GV set logo light. Now these ones were very, very interesting to me. Very, very interesting, because that seems to be exactly what I want. So in this case now, I've got some idea that gvdisplay.dll exports the functions that I'm looking for. Now, this gvSetLogoLight light was actually a complete red herring, and we'll get to that in just a minute. You'll often find that with reverse engineering projects. You think that you've cracked the case, or you go down one rabbit hole, it's a complete dead end. It's like a maze, you know? You get red herrings that look like they could be the case. It's all about testing theories, coming up with new ones. If one theory doesn't work, chuck it out, try again later. That's the entire process of reverse engineering. It's very, very frustrating, but it's incredibly rewarding if you can stick with it and get the thing to work at the end. So yeah, at this point, I'm kind of thinking, well, if there's going to be a DLL that exports the function calls I want, it's going to be gvdisplay.dll. Okay, so the next thing I wanted to go ahead and do is figure out what calls were made explicitly when I press the physical red LED change button on the actual software. So to do that, I booted the thing up in API Monitor, because now I knew kind of which DLL I wanted to monitor. I booted up API Monitor so I could actually see, well, is that DLL being called? If so, I can set a breakpoint on that DLL, and just scope out the memory that the program's using. So to do that, like I said, I used API Monitor, which is this fantastic piece of software right here. I had to use the 32-bit version because, as I mentioned, OC Guru 2 is 32-bit, but you can do all sorts of things. So like, as you can see here, you can actually set like external DLL filters, and you can choose functions from them. You can do all sorts of stuff. And then it shows you this call tree right here, where as the program's running, which DLL calls is it making in real time. And that is super helpful, because essentially, and unfortunately I can't show you this live because the dirty little secret is that this card actually died 2 years ago, and I was very sad. It started memory artifacting and then it just wouldn't post. So yeah, I can't unfortunately go back and retest my theories because the card is dead and I don't have a new one. But this is what was happening here, is I was getting, not this particular one, but I was getting calls like this that were showing up. So that's API Monitor right there. So as you can see here, yep, I enabled the GV display and GV firewire.dll ones. And there were a whole bunch of like random calls that I was getting. So like all of these ones right here were just constantly being spammed. So OC 2 was constantly making calls in the background. And so what I was looking for was, differences between this, which is what it was doing normally, and when I press the red button, because if I can get that, I can get what exactly happens. So to do that, it was kind of dumb. Like, I ended up just spamming the button, because like I said, I was just getting flooded with these like every millisecond. So I just ended up spamming the button and then stopping the execution of the program and having a look at what calls were actually being made. And it turns out, like I said, set logo light was a complete red herring. It was not actually making that call at all. It was actually making a call to a function called gv I2C. And at that point, I was like, okay, now we are getting somewhere. Because that actually tells me something incredibly useful. And top props to Gigabyte for naming their functions very descriptively. But essentially, it tells me that the communications between the control software and the LED controller on the actual GPU happens over I2C. And I'll briefly go over I2C as a protocol real quick for you guys. So as I mentioned before, I2C is one of the big three wide embedded protocols, the other two being SPI and USART. Now I have this document up here by Texas Instruments, and TI do fantastic write-ups on embedded concepts. I'm not exactly sure how useful they'd be if you have no idea about embedded stuff at all, but as somebody who already understands embedded concepts, their overview documents of concepts are fantastic. So I can definitely recommend them as a resource if you already sort of understand a decent amount about embedded systems. But I2C is a master-slave type protocol, so every data transaction that happens on the I2C bus has to be initiated by the master. There are two wires associated with an I2C bus, and this is one of the big advantages to I2C over the other embedded protocols. There's the SDA line, which is the serial data line. So in I2C, of course, it's a serial protocol, and there's the SCL line, which is the clock signal. Now, clocks, I'll actually do a separate video on clocks because clocks are really, really cool as a concept in computers, and they are incredibly vital for various reasons. And a lot of people don't even know they're a thing. But essentially, for our purposes today, a clock in a nutshell is a signal that tells the receiver when to sample information from the serial data line. So if I zoom in on this little picture here that they provided, this is a one master, multiple slave setup. So you can see here we've got an MCU, which is going to be our master, and then all of these devices over here are slaves. Now, I2C can accomplish this in 2 lines, as I mentioned before. There's actually 4 here because this is multiplexed out to 4, but you can see there's only 2 lines coming from the master. So you might be asking the question, how do you actually have so many devices on I2C if there's only 2 lines? Like, how does everybody know who is associated with which data? And it's solved because I2C uses addressing. So each one of these little slave devices here has its own address. And I have this little packet diagram right here, and you can sort of see how an I2C packet comes to be. So here we've got the SDA line and the SCL line. You can see the SCL line is doing its timing for sampling. And over here, the SDA line, there's 7 bits over here for the address of the slave. So if you think about what's actually happening back over here, all of these slaves will receive every packet that the master sends out. However, if their individual address does not match this address here, they'll just ignore it. And the address is typically programmed in at the firmware level or the hardware level from the factory on all of these devices. And if you look at the datasheet for them, it'll tell you what the I2C address is. So now if I go back over here to this packet structure, you can see that after our address bits, we've got a data frame. And now the number of data frames can actually vary, but in most cases, they've actually got an example here of reading and writing to registers. So in a lot of the cases, each slave will have some registers that you can write to. And so this is an example of what happens if you've got a register and you want to write 1 byte to it. So you can see here we've got the slave address, you've got the register that you want to write to, and you've got the data to write to that register. Now, there is an important note up here where it says it's common to have registers, but not all slave devices will have registers. So if you've only got 1 register on some controller, if you just write directly to that device's slave address with data, so like here, you can see we've only got 1 data frame, in that case, that controller might understand it perfectly. And to know that, you need to check the datasheet. And this is why I put in post at the start of the video when I commented saying, oh, this associative array is, relative to registers of the I2C controller. I don't actually know that. There's no way for me to know that, especially considering my card's dead and I can't go back and test all my theories. But the reverse engineering process here isn't what killed it. I should probably say that for the record. But I can't actually know that for sure. I might be writing to registers, like they might have a register for each color, or they might just have one register and the value I send is that, the color data. There's no way for me to know that. I can make an educated guess, but there's no way for me to know for sure. We're back here looking at OC Guru 2 now, and at this point I've set a breakpoint on every call to GV write I2C because now I know this is the function that's actually interacting with the LED controller. And what I note is that it's called 6 times when I set a static color. So when I press the red button, it calls it 6 times. But the LED change happens after the second call. So why is it doing it 6 times? At this point, I don't know, but I can probably guess it's sending additional state information, like probably the brightness and other things like that. It probably batches up all of its I2C comms and just sends it all at once. But anyway, what I'm interested in is this LED change. So that happens after the second call. Now, I can actually go ahead and investigate all of the I2C buses that the G1 exposes, because in Linux, the kernel has native support for interacting with I2C devices. You need I2C tools package in order to do this. That's at least what it was called on Arch. And then you mod probe I2C dev. That's the kernel module you load to interact with I2C devices. And there are some really nice tools provided like I2C detect. So this I2C detect program detects all of the buses, like I2C buses on your system. So if you do I2C detect -L, it'll just give you a list of the adapters. So as you can see here, I've got a whole bunch of NVIDIA ones. Now, another thing to note is that when I was breaking on this call up here, I did also notice calls to an NVAPI.dll. So that's something also to make a mental note of. But it'll be one of these NVIDIA I2C adapters here that I'm interested in. So you can go ahead, and if you call I2C detect with a particular adapter in mind, it will actually probe it for all of these slave addresses that are present on that bus. So for instance here, bus number 2, that's this one in the middle, I probed that one and I got an address at 0x48. Similarly, I did for bus 3 and I got 0x40. Bus 5 had a whole bunch of them, etc. So you can keep doing that until the end of time. But what was more interesting to me is when I actually go ahead and use I2C dump. So I2C dump is essentially, I want to read every single register on that device. And like you can give it here, as you can see, I2C dump, you give it the bus and you give it the address. I'll just make that bigger maybe so you can see. You give it the bus and you give it the address. So if I wanted to dump 0x48 on bus 2, for instance, like I do here, I2C dump to 0x48. And as you can see, I get 19 returned for the whole thing. The interesting thing about this, and this doesn't look on the surface to be that useful, but what actually happened, I got super lucky. This was the first one I tried dumping, by the way. The first one I tried, and luck is a massive thing in reverse engineering projects as well. There's no denying that. But as soon as I dumped this device, the LEDs of the graphics card turned off. So I instantly knew, okay, now I'm talking to the LED controller. So that's another thing in the process that I knew now. So what I know now is that the bus number 2 with address 0x48 is my LED controller that I can chat with now. Now, if you remember earlier, I said keep in mind we get calls to nvapi.dll, and while I was researching nvapi, I came across this right here. So this is on the nvapi reference. It's a struct called nv_i2c info v3, and there's actually a field in this called i2c dev address. And if we go to the definition for that, what you'll notice right here is this is the address of the I2C slave. It's actually, the slave address gets shifted left by 1. So here they give the example of an I2C address 0x50 stores as 0xa0 in NVAPI related calls. So if you remember, our slave address that we know now is 0x48. So if I just shift that left by 1, you can see here we're looking for 144, which is actually 0x90. So in the NVAPI related stuff, I'm looking for 0x90. So come down here a little bit, you can see I referenced that NVAPI thing in my paper, but now I want to take a deeper look at each call to this particular function. So I break on it, and this time I'm actually going to expand these little menus here and have a look at the memory of the program. So if I expand out this particular menu here, You can see here we've got a reference to a memory address at 0x0018E124, and there's another reference down here to 18E190. So those are both things that I want to investigate. So if I have a look to that memory address at this particular point in time, you can see this is really, really interesting, guys. What's that right there? That at the exact memory address that we saw in that function call to gvwrite I2C is 0x90, which is our slave address that we found right before that we were interacting with, shifted left by 1 as per the NV API documentation. We have the address as 0x90. So it's probably safe to say that this argument right here is the slave address. So that's really, really useful. For this particular one, I was looking at cyan as the color. But we go back down, and what I noticed, and this is something that I wanted to do, I wanted to look at the memory around this region every time I tried a different color, and I wanted to see what was different about the memory in this region when I tried a different color. So I tried a few different colors, and I found that at 18E12C is where I actually found a change. So for blue, it was 14. For red, it was 11. For green, it was 12. These are hex values, of course. For magenta, it was 15. Cyan was 16. And white was 17. So now I have some very interesting information. I have that the address that I'm looking for is confirmed. So it's bus2, address 48. And now I've got different values that are being stored in memory and presumably passed to gvwrite I2C. When I try to change the color. So now I just did the dumbest thing ever, and I just tried using I2C set, which is a Linux built-in function, and I'll get the man page up for it right here. So you can see here, it's I2C set, the bus, the chip address, and the data address. So if you remember from way back here, you know, you've got the register address and the data that you want to write. So that will correspond to, like, the chip address is the slave address, data address would be the register, and then you've got the value that you want to write. So I just did the most brain dead dumb thing, and I was just like, okay, can I just write to this address and try and replicate these calls here? And so I did. And I just wrote, so, you know, I wanted to change it to, what's 14? 14 is blue. So I wanted to change it to blue. So I noticed that the value here for each call was getting cycled between, you know, 14, 81, 83, 14. And so essentially this worked perfectly. I was very surprised. This was like the first thing I tried. I just wrote that value to the slave address and it worked. Technically, now this is where the sort of ambiguity comes in. You'll notice that the function, so the call here corresponds to, so the chip address obviously is 48, the data address is 14, and then the value is 0x00. So potentially this call, and I can't go back and test this theory, but it might be the case that there's a different register here that I'm writing to with this value 0, and that determines the color. Or it could be that this LED controller does not actually have a an address like multiple registers to write to, and I'm just sending this data right here, and it just accepts that and ignores this 0x00 value for the second data frame. So it could be either. I don't actually know. All I know is that this works, so that's good enough for me. And if I go back down, I actually found a simplification where I could just write the exact, you know, value here a bunch of times that for the color that I wanted, and that worked fine. I didn't have to bother with 81 or 83. I just wrote this 4 times and it worked. This is the entirety of the output for that project. It's just associative array with the values here, and it does that 4 times. This was the output of an entire week's worth of work on my part. I spent about 5 days on this project in total. I was pretty much working the entire time. I had nothing to do back then, so I was working on this the entire time, and all for 9 lines of shell script. I had a bit more fun with it, and I wrote this. So this is a color randomizer, right? So OC Guru also had a randomizer button that you could click, and every couple of minutes, or sorry, every couple of seconds, it would change the color. So I just went and replicated that. I've got a sleep interval. It doesn't pick the same color twice. It's pretty neat. So yeah, that's essentially it for this video, guys. I'll link all of the documentation in the description below. If you've done any cool hardware reverse engineering projects, I'd really love to hear about them. And thanks so much for watching this video.